Today we're going to look at relations. Relations are one of the most important mechanisms that we have in our math toolkit for proofs. We'll start with some simple examples, and then in later videos we'll be looking at more interesting applications. So, relation is basically a connection between objects. We could have binary relations with two objects related, ternary relations, three objects. Look, if we understand two objects, we're all good. Here are some examples. You can define a relation. A relates to B if A squared is equal to B, okay? Or a relation, these two numbers will relate to each other if the absolute value of one is equal to the other, great. Or we could even have English written examples, okay? So these two people are related to each other if they live on the same street. Fine, makes sense. Down here, this is something called a floor function, which is just basically rounding down, okay? Another cool thing about relations is we can write them as pairs. So for example, looking at relation 1, you can say okay, here are some examples, because 1 squared is 1. That is the same as writing just the tuple 1 comma 1. 2 squared is 4, so this is perfectly fine, and you square negative numbers and they work as well. Great. So this is kind of a compact notation for this relation. But there's something else which is really important, and that is equivalence relations. Okay, so equivalence relations, special sort. We have three properties that we have to satisfy. First property is called reflexivity. Okay. So for every element of the set that we're imposing the relation on, the element relates to itself. Second one is symmetry. Okay. So for any two elements that I pick in my set, if one relates, if A relates to B, then that implies that B must relate to A. It's the transitivity. Okay, so if I pick any three elements, A, B, and C, and A relates to B, and then B relates to C kind of separately, then it's also true, this implies that A relates to C. So it kind of flows through. Okay, great. So let's look at the four examples that I put here, and we'll say, are they equivalence relations? Well, let's look at relation 1. Is it reflexive? No. Okay, so not reflexive. We have element 1 relates to itself, but that's the only case, okay? So we can say the element 2, 2 does relate to 4, but 2 does not relate to itself. Okay. So, not an equivalence relation. Number 2. Let's see. Well, reflexivity depends, right? So, okay. So, it doesn't work on negative numbers, right? So if I put in a negative number and I take its square root, sorry, not square root, take its absolute value, it becomes positive. So it's not equal to its own absolute value. But if we have positive numbers, that's fine. Remember that the definition of absolute value is defined as a piecewise function. If the number that I put in is positive, it makes no difference to it, okay? But if the number can be 0 as well. If the number I put in is negative, then it multiplies by -1 to produce a positive answer. So the only case where we're good is in the positive or 0 case, okay? So it's reflexive on this domain here. Let's check again. Is it symmetric? Well, look, applying absolute value to positive numbers, we're not changing them at all. So we put in 2. 2 relates to 2, and therefore 2 relates to 2. So it's a bit of a silly example, but it's true. Okay, so that works. Is it transitive? Well, yes. Okay. Because really, if we're just considering positive numbers, including 0, then the only time a number will relate under relation 2 is if they're exactly equal. How about 3? Reflexivity. Well, pick a person, right? Me. Do I live on my own street? Depends how you define this, but it's reasonable to say, yeah, every person lives on their own street, so it's reflexive. Is it symmetric? If I live on the same street as you, does that mean you live on the same street as me? Yes. Okay. Is it transitive? Okay. I live on the same street as you, and you live on the same street as Tim from accounts. Okay. Then me and Tim from accounts, yeah, we're totally on the same street. So 3 is an example of an equivalence relation. 4. Okay, so I'm using the floor function. Does every number relate to its own floor? Yes. So just as an example, let's say I put in 1.1, find the floor of that. That rounds it down to 1, which, you know, it's... Okay, perfect. Okay, so number relates to itself. 2, is it symmetric? Okay, well, let's pick an example. Let's say I have -0.7. This operation rounds us down to -1, and that will be the same as rounding down -0.2. Okay, but if I reverse the order, it still works. So that's fine, that's good. So it's symmetric. Is it transitive? Well, yeah, absolutely. So let's say we have another case, -0.2, and that, yep, relates to, okay, well then we can totally say that our initial number, you know, the chain links through, yeah, it still relates. So number 2, 3, and 4 form equivalence relations. Number 2, we have to restrict the domain, but the rest of them work just fine. Okay, so let's say we have an equivalence relation and we're defining it on some sort of set, okay? Then, as I said here, it partitions that set into little proper subsets. So just to remind you, a partition is a bunch of subsets that when you take the union together, they reconstruct the full set, and each of them are mutually exclusive, so they have no overlap with each other. Now, each equivalent class is defined as kind of the set of elements which all relate to each other under this equivalence relation. Let's look at some examples, okay? So for this one, if we put in a number, and you know we're on an equivalence relation, so we need to be like a proper, you know, positive or non-negative number. There's just one element which relates. Every number just relates to itself under relation 2. If we take relation 3, then for example, take the equivalence class of John. This is a set of all people who relate to John under relation 3, which is just everyone who lives on his street. So, you know, and note that because all of these people live on the same street, you know, we could just pick one to represent the equivalence class, which is what I've done here. But it doesn't matter which one we pick, so I could pick John, Mary, or Tim, or anyone else on the street. Now equation 4, relation 4 is a little more complicated, but it's fine. So what do we have? Let's say we pick a number A, and I'll give you an example here. Okay, so let's say we pick 1.8. Well, what happens to 1.8? It rounds down to 1. And let's look at 1. Okay, so we look at 1 and it rounds down to 1 as well. So we look up and up, you know, 1.9, 1.99. Because of the floor relation, they're all rounding down up to 2. Okay, but 2 doesn't round down, it just stays as 2. So we have open point, so we're not including that. Okay, so we're including everything from 1, including 1, not including 2. Okay, so we're dealing with real numbers, and what we've got here are intervals. By the notation here, square bracket is we're including the lower point, excluding the upper point, and that's exactly the same as this diagram. Cool. Okay, so hope you had fun. These were just some basic examples. In later videos, we'll be actually using this to do some interesting things. All right, cool. Have fun. See you later.